Welcome to the deep dive. Today, we're digging into a whole stack of resources, all center around this idea of Flutter engineering.
Right.
Look, knowing how to write Flutter code, that's one thing, but building apps that are genuinely robust, scalable, high quality,
That takes more.
yeah, that takes an engineering mindset. So our mission here is to pull out the most important principles, patterns, practices from this material, really focusing on the insights that will help you make that leap.
Absolutely.
We're going from, the fundamental building blocks, architecture, all the way through things like security, testing, making apps feel right on any device.
And it's a critical distinction the sources make, isn't it? Building software isn't just syntax or, slapping widgets on a screen.
No.
It's the underlying structure, the decisions you make so it's maintainable, reliable as it grows. It's really about applying that engineering discipline.
Okay, so let's jump right into that core idea then. The shift from just, programming to actual engineering. What's the foundational principle they really hammer home?
Well, at the heart of it, it's separation of concerns.
Okay.
Think of it like organizing your desk.
Right.
You don't just dump everything in one big pile.
Hopefully not.
You break your app down into distinct areas, each responsible for just one specific job.
Yeah.
And closely related is modularity.
Right, making things into interchangeable bits.
Exactly, dividing systems into neat, interchangeable modules.
And Flutter's core structure, the widget tree, that seems almost, perfectly designed for this, doesn't it? Each widget is kind of its own little self-contained piece.
It really is.
Yeah.
Flutter's widget-based architecture is inherently modular. A widget encapsulates a specific part of the UI, maybe some functionality. It aligns directly with separating concerns.
Okay.
You can think of having distinct layers, UI, business logic, how data gets processed, data management. All separate, but talking in structured ways.
And why? What's the danger if you don't?
Because in Flutter, if you mix all that logic together, you often end up with these massive, totally unmanageable widgets. What developers affectionately call widget hell.
Widget hell. Doesn't sound fun.
It's not. So separation of concerns is your first step out.
Okay, so widgets aren't just visual things, they're encapsulated units, logic and UI. And the sources then bring up design patterns.
Yeah, design patterns. These are like proven blueprints, solutions for common recurring problems you see again and again in software design.
Reusable templates.
Reusable templates, exactly. Applying them systematically leads to code that isn't just working now, but is also reusable, much easier to maintain, and, crucially, more flexible when requirements inevitably change.
So instead of reinventing the wheel every single time, you grab a recognized pattern. Could you maybe give an example? How does a pattern actually do that?
Sure. Let's take the observer pattern. Imagine you've got some data that changes, right? And multiple parts of your UI need to update when it changes.
Okay, common scenario.
Very. So you don't want each UI piece constantly asking, has the data changed? Has it changed now? With the observer pattern, the UI pieces just subscribe to the data source. They listen. And the data source automatically notifies all its subscribers whenever it changes.
Efficient.
Very. It means the UI doesn't need to know how the data changes or where it even comes from. It just reacts when it gets the notification.
Yeah.
That's key for achieving loose coupling and flexibility.
That clicks. Data changes, everyone listening gets an automatic ping. Oh, okay, cool. Let's dive inside Flutter's rendering system itself then. The source uses this really nice analogy, thinking of your app like a sophisticated Lego masterpiece.
Yeah, built from smaller, specialized widgets. It's a great visual.
It is. And how Flutter actually positions those Lego pieces on screen, that's quite specific, isn't it?
It is. It uses a constraint system. It works like this. The parent widget passes constraints down to its children.
Like rules.
Essentially saying, okay, you can be anywhere between this minimum and maximum size. The child then figures out its own size within those constraints.
Okay.
And finally, the parent sets the position. So constraints go down, sizes come up, parent sets the position.
Constraints down, sizes up, parent positions. Got it. And beneath the widgets we actually code with, there are these three primary trees working together.
Right. The widget tree, the element tree, and the render object tree.
Let's break those down. Widget tree first.
Okay, the widget tree is what you, the developer, mostly interact with. These are your stateless widgets, your stateful widgets. It's the declarative configuration of your UI at any given moment.
Like the blueprint.
Exactly. It's the blueprint of what you want the UI to look like right now.
So the widget tree is our high-level design. The what? What about the element tree? What's its role?
The element tree. This is where a lot of the efficiency magic happens. It sits between the widget tree and the render object tree.
Okay.
Now, Unlike widgets, which are immutable, they just describe the UI at a point in time. Elements are long-lived and mutable.
So they stick around?
They stick around. They manage the life cycle of the widgets, and they hold on to the associated render objects.
Mm.
The stability of the element tree is absolutely crucial for performance.
How so?
Well, when your widget tree changes, because, say, the state-updated Flutter compares the new widget tree to the stable element tree, it figures out the absolute minimum set of changes needed to update the UI.
Smart.
Very smart. It reuses existing elements and render objects whenever possible. This comparison and reuse is fundamental to how Flutter stays so fast.
Okay, that makes sense.
And that build context you use everywhere in your widgets, that's actually implemented by the element class. It's basically a handle, a reference to the location of a widget within this element tree.
Wow, okay. So the element tree is the real performance workhorse, managing updates efficiently.
Yeah.
And the third tree, the render object tree.
That's the render object tree. This is where the actual, well, pixels meet the screen, metaphorically speaking. Layout calculations happen here, painting happens here.
The geometry.
Exactly. The geometry, the positioning, the appearance of everything. When you need really low-level control over drawing maybe a custom chart, complex visual effect, you might work closer to this layer, perhaps using something like a custom painter.
And that interacts with this tree.
Yeah, it interacts with the render object system to tell it when things need recalculating, like Mark needs layout or Mark needs paint.
Got it. So this confirms Flutter isn't just, wrapping native UI components like some other frameworks. It's drawing everything itself.
Precisely. Flutter compiled your Dart code directly to native machine code ARM by 64 and renders the UI using its own high-performance graphics engine, Skia.
Skia, right.
It completely bypasses the platform's standard UI libraries, like UIKit on iOS or Android's views.
Which is why it looks and feels so consistent across platforms.
That's a huge part of it. And it challenges that traditional idea of what native even means. It is native machine code, running directly on the processor, but it's not using the platform's native UI toolkit.
That's a really key distinction. Okay, speaking of performance, the sources talk about Dart's concurrency and parallelism features. Why are those so important for keeping an app feeling responsive?
Oh, they're critical, because the golden rule is never block the UI thread.
Right, that's what causes jank, frozen apps.
Exactly. So Dart handles concurrency for asynchronous tasks, things that take time but don't need intense computation, like fetching data over the network. It uses futures and streams for that.
So the app can do other things while waiting.
Precisely. But for really heavy computational work, like processing a huge image, doing complex math, you need parallelism. You need to actually run code simultaneously.
Okay.
And Dart provides isolates for this. Isolates are like separate workers with their own memory. They don't share memory with the main UI isolate.
Ah, so no blocking.
No blocking. You can offload that intense work to a separate isolate, let it crunch the numbers, and it won't freeze up your user interface. Essential for smooth apps.
Okay, keep heavy lifting off the main thread using isolates. Makes sense. Now, let's maybe move up a level from the core mechanics to structuring the whole application. The sources clarify this difference between architectural styles and design patterns.
Yes, that's a good distinction to understand. Architectural styles are the really high-level blueprints for the entire system. Broad concepts like, say, a layered architecture, separating UI, business logic, data layers. Or maybe an event-driven style.
Big picture stuff.
Big picture stuff. Design patterns, on the other hand, are more specific, localized solutions for those recurring problems within an architecture. Like how objects get created that might be a factory pattern, or how components communicate maybe the observer pattern we talked about.
So architecture is like the city plan, and design patterns are the blueprints for, specific types of buildings within that city, like houses, offices.
That's a great analogy.
Okay.
Exactly. And the source material really emphasizes the importance of architectural thinking.
More than just picking a pattern.
Much more. Architectural thinking is about understanding the system as a whole, the ecosystem it lives in, making informed decisions, and critically analyzing trade-offs.
Trade-offs again?
Always trade-offs. The source even calls this the first law of software architecture. Everything in software architecture is a trade-off. You're constantly balancing things, performance versus development speed, maintainability versus initial complexity, flexibility versus simplicity.
Ah, the eternal balancing act.
Yeah.
And related to that, they stress avoiding over-engineering, right?
Oh, definitely.
Yeah.
It's so easy to get excited about complex patterns or elaborate architectures you read about. But you need to balance that complexity with simplicity.
Keep it appropriate.
Exactly. For a small, simple app, maybe adding 5 layers of abstraction is just overkill. A basic layered structure, maybe just using set state for state management, could be perfectly sufficient.
Don't build a skyscraper if you only need a garden shed.
Precisely. Over-engineering introduces unnecessary complexity, slows you down, makes things harder to understand.
Good reminder. Okay, so what are some common UI architecture patterns the sources discuss specifically for Flutter apps?
Well, two prominent ones that come up a lot are BLOS, that's business logic component, and MVVM, model view model.
Okay, BLOSI first. What's the core idea?
BLC focuses on separating your business logic completely from the UI. It uses a reactive approach. Widgets dispatch events like button tapped or text entered to the BLC.
Okay.
The BLC processes these events, does its logic, and then emits state changes like loading data or data loaded via streams.
And the UI listens to these streams.
Exactly. Widgets subscribe to these state streams and rebuild themselves whenever a new state is emitted. It creates this clear flow. UI sends events in, listens for states coming out.
So BLOSI is all about inputs, events, and outputs, states via these streams. Makes sense. What about MVVM?
MVVM is also very popular, especially for people coming from other platforms, maybe. Here, the view your widgets interacts with a view model.
Okay.
The view model holds the UI state and interacts with the model that's your data layer, your core business logic. Changes in the model usually notify the view model, which then updates its state, causing the view to update.
So view talks to view model talks to model changes flow back up.
That's the general flow. Both BLOC and MVVM aim to separate concerns, make the UI more testable, more maintainable. And they both synergize quite well with Flutter's reactive nature, the UI automatically updating when underlying data changes.
And the sources mention others too.
Yeah, briefly. Things like MVI, model view intent, Viper, ribs. These were often variations on the theme, maybe focusing more strictly on unidirectional data flow or defining even more granular layers for very large, complex applications.
Wow, okay. It sounds like there are quite a few options. How on earth do you choose the right one?
Well, that's where that architectural thinking comes back in. The sources really stress there's no single best pattern.
No silver bullet.
No silver bullet. The right fit depends entirely on your project's specific requirements, the size and experience level of your team, the long-term vision for the app. Sometimes a simpler pattern is genuinely better. Sometimes you need that more structured approach for scale. It's always a trade-off.
Always a trade-off. Okay, that moves us nicely into talking about building quality into the app itself, starting with what the source material cheekily calls a controversial topic, state management.
Yes, the endless state management debates in the Flutter world.
It seems like it. How do the sources help clarify this?
Well, they start by making a useful distinction between local state, sometimes called ephemeral state, and global state.
Okay.
Local state is UI state that only matters within a single widget or a very small part of the widget tree. Think like, is an animation running? Is a text field focused? Is a checkbox checked? Often you can handle this perfectly fine just using set state within a stateful widget.
Simple enough.
Simple enough. Then there's global state or app state. This is data that needs to be accessed or shared across many different widgets, maybe across different screens.
Like the logged-in user's profile.
Exactly. Or the contents of a shopping cart, application settings, that kind of thing.
And that's where all the different solutions come in, right?
That's where it gets interesting, yes. Flutter itself has built-in mechanisms. Inherited widget is the foundation, and things like change notifier used with listable builder are built on top of that. These are perfectly capable, especially for simpler global state needs.
But there's more out there.
Oh, yes. The ecosystem has a vast array of third-party packages for state management provider, Riverpod, Belong Flutterblock, MobX, GetX, ZooStand. The list goes on.
So how do you choose?
Again, trade-offs. The sources suggest looking at factors like how complex is your state? How much boilerplate are you willing to write or avoid? What's your team already familiar with? Even things like package popularity, community support, and the quality of documentation matter.
Makes sense.
They use Riverpod as one example in the material, showing how it uses this concept of providers to manage not just state, but also dependencies in quite a robust and testable way.
Okay, speaking of dependencies, let's talk about dependency injection, DI. Why is that concept important?
Dependency injection is really a fundamental principle for building loosely coupled, maintainable software. The core idea is inversion of control.
Okay, what does that mean in practice?
It means that instead of a component creating the things, it depends on itself.
Like a screen creating its own network service instance.
Exactly. Instead of doing that, the component receives its dependencies from an external source. It doesn't build them, it asks for them, or they're injected.
So what's the big benefit of doing that? Why bother?
The main benefit is loose coupling. Your components aren't tightly tied to specific concrete implementations of their dependencies.
Ah, flexibility.
Flexibility, yes. And, crucially, testability. It makes your code much easier to test. In your tests, you can easily inject a fake or a mock version of a dependency, like a mock database service that returns predictable data instead of needing the real thing.
Right, so you can test components in isolation.
Precisely. It also makes your code more modular, easier to refactor, easier to swap out implementations later if needed.
How do you actually do DI in Flutter?
Well, the simplest way is just passing dependencies through constructors, constructor injection. Flutter's built-in inherited widget can also be used as a basic DI mechanism. And as we mentioned, many state management packages, like Provider or RiverPod, naturally incorporate DI features as part of how they work.
Okay, so DI is pretty essential for testable, flexible code. Got it. Now, the source mentions a pretty complex topic, offline-first architecture, building apps that work smoothly even without internet.
Yeah, this gets highlighted as being inherently complex and requiring, well, significant engineering effort. It's not trivial.
What are the main challenges?
The sources point to things like, how do you ensure data integrity when changes are happening offline? What happens when the connection comes back? How do you synchronize the local changes with the server?
Conflict resolution.
Exactly. What if the same piece of data was changed both offline and on the server while you were disconnected? You need strategies to resolve those conflicts, maybe based on timestamps, versioning, or even asking the user. Very. And you also need to manage operations that couldn't be sent immediately, maybe queuing them up reliably. It's a totally different mindset compared to building an app that just assumes it always has a connection.
You're essentially managing two potential versions of the truth and figuring out how to reconcile them. That sounds hard.
It requires careful planning, that's for sure.
Okay. And how do Flutter apps actually talk to the underlying native platform features? Things like the camera, GPS, sensors.
That's primarily handled through platform channels. This is Flutter's built-in mechanism for sending messages back and forth between your Dart code and the native platform code, Swift Objective-C on iOS, Kotlin Java on Android.
So you write a bit of native code to handle the platform API?
Usually, yes.
Yeah.
Or you use a plugin that someone else has already written, which uses platform channels under the hood. It lets you access pretty much any native API.
And for lower level stuff?
For really low-level integration, maybe with existing CC++ libraries or a complex game engine, you might use Dart FFI, the foreign function interface, or JNIgen for Java native interface bindings. That lets Dart code call directly into native code libraries.
Okay, that covers a lot of the internal mechanics and structure. Let's shift gears a bit and talk about the team aspects, collaboration, code quality across a whole project.
Right, because apps aren't usually built by just one person. Collaboration is key.
Yeah.
And the bedrock of that, really, is robust version control.
Git, usually.
Almost always Git these days, yeah. And the sources discuss different branching strategies for managing code changes within Git, like feature branching, where each new feature or bug fix is developed on its own isolated branch before being merged back.
Keeps things separate.
Keeps things separate. Reduces conflicts on the main line. Another approach mentioned is trunk-based development, which involves everyone working directly on or very frequently merging into the main branch, the trunk.
Faster integration, potentially.
Faster integration, less complex merge histories, but requires very strong automated testing. Git flow is also mentioned as a specific, more structured flavor of feature branching, often used in larger projects with formal release cycles.
And integrating testing and automation into that whole process seems crucial for team efficiency.
Oh, absolutely essential. That's where CI/CD comes in: continuous integration and continuous delivery or deployment.
TI first.
Continuous integration means automatically building your app and running your tests every time someone pushes a code change to the shared repository.
So you get immediate feedback.
Immediate feedback. If you broke something, you know right away, not days later. It helps maintain the integrity of the codebase constantly.
And CD?
Continuous delivery or deployment automates the process of getting that tested, integrated code out either to testers or maybe even directly to production users. It makes releases faster, more reliable, less of a manual chore.
And integrating your tests into that CI/CD pipeline is basically non-negotiable.
Absolutely. Unit tests, widget tests, integration tests, they should all run automatically in your CI pipeline. Tools like Fastlane are also mentioned, which help automate common mobile development tasks like building, signing, and deploying apps.
Automation catches problems early, keeps things smooth. How do the sources suggest maintaining code quality within that automated process, beyond just passing tests?
They strongly advocate for using code quality tools and establishing clear practices. This really starts with having agreed-upon style guides or guidelines.
Like the official Effective Dart guide.
Exactly. Effective Dart, effective Flutter guides. These provide great baseline rules for writing clean, readable Dart code.
And tools to enforce it.
Yes. Using static analysis tools is key. Dart Analyze is the built-in tool, often configured with custom rules in your analysis options, the YAML file using linters. These tools automatically catch potential code grammatic errors, style issues, anti-patterns before the code even runs.
Catches things linters find.
Right. And code formatters, like the standard Dart FMT, ensure everyone's code looks consistent stylistically, which really helps readability.
Takes the arguments out of formatting.
It does. The sources also suggest maybe creating custom internal tools or scripts, perhaps using Git hooks to enforce specific project standards automatically, like checking commit message formats or running extra checks before allowing a push.
Tools enforcing the rules makes a lot of sense for consistency. Okay, now a really big topic. Testing. The sources seem to dedicate significant attention here.
And rightly so. Testing is how you build confidence that your app actually works as expected, and crucially, continues to work as you make changes over time.
Peace of mind.
Huge peace of mind. The sources describe the classic testing pyramid.
Ah, yes, the pyramid.
Right? At the broad base, you have unit tests. These are fast, isolated tests of individual functions, methods, or classes. They don't involve any UI or external system.
Brick and sheep.
Quick, cheap to write and run. Above that, you have widget tests. In Flutter, these let you test a single widget, or maybe a small group of interacting widgets, in isolation from the full app. You can interact with them, check their appearance.
Still pretty fast.
Still relatively fast, yeah. Then you have integration tests. These test larger parts of your app working together, maybe involving multiple screens, state management, even simulated network calls.
Verifying the connections.
Verifying the connections between different parts. And finally, at the narrow top of the pyramid, you have end-to-end E2E tests. These drive the entire application, often through the actual UI, simulating a real user's journey from start to finish.
So the idea is lots of fast unit tests at the bottom, fewer, slower, more comprehensive E2E tests at the top.
Exactly. It's that trade-off again. Unit tests are fast, stable, easy to write, but they give you relatively low confidence that the whole system works. E2E tests give you very high confidence, but they're slow, often brittle, they break easily with UI changes, and expensive to write and maintain.
So you need a balance.
You need a balance. Hence the pyramid shape. Invest most heavily in unit and widget tests. Have a good layer of integration tests, and a smaller number of critical E2E tests for key user flows.
Makes sense. The sources also talk about test doubles, using stand-ins during tests.
Yes, test doubles are essential for isolating the code you're testing from its dependencies. Like stand-ins in a movie. That's a good way to put it.
What kinds are there?
The sources give examples. Stubs are simple doubles that just provide pre-canned answers to calls, like a fake network service that always returns specific predefined data when asked.
Okay.
Mocks are a bit more sophisticated. There are objects you set expectations on.
Yeah.
You might use a mock to verify that a specific method on a dependency was called exactly once, with certain arguments. They're about verifying interactions.
Checking behavior.
Checking behavior, right. And dummies are the simplest. They're just placeholder objects passed around when an argument is required by the code under test, but its value doesn't actually matter for that specific test. Got it.
Stubs give data, mocks check calls, dummies fill space.
That's a good summary. They also mention an interesting principle in testing. DAMP-ED. Descriptive and meaningful phrases.
DAMP. I thought the mantra was always DRY, don't repeat yourself.
Good point.
Yeah.
DAMP is slightly different and applies specifically to test code. In production code, yes, we strive to minimize repetition, DRY. But in tests, sometimes repeating a little bit of setup code within each test is actually okay, even preferred.
Why is that?
Because it makes each test completely self-contained, explicit, and easy to understand just by reading it. You don't have to jump around to figure out shared setup logic. DAMP prioritizes the readability and clarity of an individual test case over strict code reuse, because understanding what a test is verifying quickly is paramount.
Ah, okay. Clarity over absolute conciseness in tests. That makes sense.
And the key, again, is integrating all these different levels of tests, unit, widget, integration into your CI/CD pipeline so they run automatically and give you that continuous validation.
Right. And finally, on the process side, documentation. The source makes a really strong case for treating it seriously, not as an afterthought.
They really do. Documentation is absolutely critical, though often undervalued or neglected. It's how knowledge gets shared within a team, how new developers get onboarded effectively, and how the app remains maintainable over the long term.
Hard to maintain what you don't understand.
Exactly. Flutter's own extensive documentation is held up as a good example. Clear terminology, lots of helpful code samples, even linking to live examples or videos sometimes, focusing on providing valuable insights, not just API listings.
Quality docs matter.
Hugely. And the source specifically warns against the perils of outdated documentation. There's almost nothing worse than documentation that lies to you because the code has changed and the docs haven't kept up.
Misleading.
Very. The strong recommendation is to treat your documentation like code. Keep it in version control, update it regularly as part of the development process, review it.
Docs is code. I like that. Okay, that really covers the development process side well. Now let's talk about polishing the final app, making sure it's secure, private, accessible, and looks good everywhere. Starting with security. Crucial topic.
Absolutely foundational. Non-negotiable for any real-world application. The sources introduced the classic CIA triad as the core security principles.
The CIA.
Confidentiality, integrity, and availability. Confidentiality is about keeping data secret from unauthorized eyes. Integrity is ensuring data hasn't been tampered with or altered inappropriately. Availability is making sure the app and its data are actually accessible and functional for legitimate users when they need it.
The three pillars.
The three pillars. And they discuss addressing common vulnerabilities, often referencing the OWASP Top 10 list, a standard awareness document about the most critical web and increasingly mobile application security risks.
Okay, what are some specific risks they highlight that Flutter developers really need to be aware of?
Well, several come up. Supply chain vulnerabilities. That means risks coming from the third-party packages and dependencies you pull into your app. Are they secure? Have they been compromised?
Something you have to track.
You do. Input validation and sanitization is huge, making sure any data coming from users or external sources is properly checked and cleaned to prevent things like injection attacks, SQL injection, cross-site scripting.
Don't trust input.
Never trust input. Avoiding insecure communication, meaning always use HTTPS for network requests to encrypt data in transit. Addressing insecure data storage, don't store sensitive stuff like passwords or API keys in plain text locally. Use secure storage solutions like the Flutter Secure Storage package.
Right.
And also insufficient binary protection, things like using code obfuscation to make your compiled app harder to reverse engineer, and generally minimizing sensitive logic stored directly in the client-side binary.
And cryptography comes into play here too.
Definitely. Cryptography provides the underlying tools. The sources briefly touch on concepts like symmetric encryption, using a shared secret key, versus asymmetric encryption, using public-private key pairs, hashing, creating fixed-size fingerprints of data to check integrity, digital signatures, using private keys to verify authenticity, and key derivation functions, KDFs, for securely generating encryption keys from passwords. These are the building blocks for achieving confidentiality and integrity.
Security is definitely complex, but clearly essential. What about the related topic of privacy?
Privacy is becoming increasingly important, driven partly by regulations like GDPR in Europe or CCPA in California, but also just by growing user awareness and expectations.
People care more about their data.
They do. The source strongly advocates for privacy by design, or PBD. This means integrating privacy considerations into the entire development lifecycle right from the start, not just tacking it on at the end.
Proactive, not reactive.
Exactly. Key practices include things like data minimization, only collect the personal data you absolutely need for a specific purpose, obtaining clear, informed user consent before collecting or processing personal data, and ensuring secure logging, being very careful not to accidentally log sensitive personal information where it shouldn't be.
And building a culture around that.
Yes, building a privacy-aware culture within the development team is really key to making it stick.
Okay. Moving from privacy to making sure everyone can actually use the app, accessibility, often abbreviated A11Y.
Accessibility is crucial. It's about designing and building apps that are usable by people with a wide range of disabilities, visual impairments, hearing loss, motor difficulties, cognitive differences.
It's not just a niche requirement.
Not at all. And honestly, making your app more accessible often makes it better for everyone. It's not just about compliance. It's about inclusion and good design. The sources introduced the WCAG Web Content Accessibility Guidelines principles as pillars.
WCK, right. What are those principles?
They're often remembered by the acronym POUR. Perceivable, operable, understandable, and robust.
POUR. Okay, perceivable.
Can users perceive the information being presented? This involves things like providing text alternatives for images, using Flutter's semantics widget, ensuring sufficient color contrast, not relying solely on color to convey information.
Operable.
Can users interact with all the controls and navigate the UI? This means supporting keyboard navigation, providing large enough touch targets, avoiding keyboard traps, managing focus properly.
Understandable.
Is the information presented and the way the UI operates clear and predictable? Using clear language, consistent navigation, providing helpful error messages.
And robust.
Can the content be reliably interpreted by a wide range of user agents, including assistive technologies like screen readers? This often means using standard components correctly and providing the right semantic information.
How do you actually implement these things in Flutter? What are the tools?
Flutter has pretty good built-in support. The semantics widget is your primary tool. You wrap your regular widgets with semantics to provide extra information labels, hints, actions, whether something is a button or a header that assistive technologies like TalkBack or VoiceOver can understand and announce.
So you annotate your UI.
You annotate your UI for accessibility, yes. Implementing proper keyboard navigation and focus traversal is also crucial, using widgets like Focusable Action Detector and Focus Traversal Group to control how users move through the UI without a touchscreen.
Anything else?
Considering animations is important too, offering an option for reduced motion for users sensitive to it. And critically, you need to test accessibility. Use the built-in analysis tools, test with screen readers turned on, and if possible, get feedback from users with disabilities.
Manual testing is key there.
Okay.
And then there's adaptive design, making the app not just resize, but look and feel right on different types of devices and platforms.
Exactly. Adaptive design goes beyond just responsive layout, making things fit on different screen sizes. It considers the whole context. Screen size, yes, but also orientation, portrait landscape, input method, touch, mouse, keyboard, stylus, and even platform conventions and expectations.
So an app might behave differently on a tablet with a keyboard versus a phone.
It should, ideally. It's about creating experiences that feel natural and optimized for the specific device context. This involves handling different screen sizes and resolutions effectively, of course, but also adapting layouts based on available width, maybe showing a two-pane layout on a tablet, but a single list on a phone.
And input methods.
Adapting to input methods is crucial, making sure keyboard navigation works smoothly for desktop or web users. Handling mouse hover effects where appropriate. Adapting drag and drop interactions depending on whether it's touch or mouse input.
What are some specific Flutter widgets that help with this kind of adaptation?
The sources mention several key responsive and adaptive widgets. Layout Builder is fundamental. It gives you the exact constraints, width and height, of the parent widget, letting you decide what layout to build based on that size.
So you can switch layouts based on width.
Precisely. Orientation Builder helps adapt based on whether the device is in portrait or landscape mode. Flexible and expanded are essential for distributing space within rows and columns flexibly. Wrap is great for layouts that need to flow onto multiple lines if space is tight. The concept of using breakpoints, specific width thresholds to trigger layout changes, is also common practice.
Okay, that makes sense. And of course, there's handling different languages and regions.
Right, internationalization, I-18N, and localization, L10N. Internationalization is the process of designing and writing your app so it can be adapted to various languages and regions without needing engineering changes.
Preparing the app.
Preparing the app. This involves using packages like Flutter localizations and IntelliChannel, externalizing all your user-visible strings into resource files, like ARB files, and using APIs that handle locale-aware formatting.
And localization.
Localization is the actual process of doing the adaptation for a specific locale, translating the text strings, formatting dates, times, numbers, currencies according to local conventions, handling plurals correctly, sometimes even adjusting layouts or images for cultural appropriateness.
A lot goes into that, and making it look consistently on brand across the whole app, theming and styling.
Flutter's theming system is quite powerful, especially within Material app or Cupertino app. You can define things like your app's color schemes, typography, fonts, text styles, and visual density centrally in a theme data object.
And widgets use that theme.
Yes, standard Material or Cupertino widgets automatically adapt their appearance based on the theme provided. This ensures a consistent look and feel across your application and makes rebranding or supporting dark mode much easier. The sources also note the evolution from Material 2 to the newer Material 3 design guidelines, which offer even more sophisticated theming options.
Good to know. Finally, the source just touches on custom painting and shaders for really advanced visual stuff.
Yeah, this is for when the standard widgets aren't enough. Custom Paint, combined with a custom painter class, gives you direct access to a canvas object.
Like a drawing board.
Exactly. You can draw arbitrary shapes, lines, paths, images directly onto it, pixel by pixel if you need to. This is great for highly custom visual elements like complex charts, unique animations, or graphical effects. And sometimes, for specific types of drawing, it can even offer performance benefits.
And shaders. That sounds even lower level.
It is. Shaders allow you to write small programs that run directly on the device's GPU, graphics processing unit. You write them in a shading language like GLSL. They're vertex shaders, manipulating geometry, and fragment shaders, determining pixel colors. This gives you ultimate control for things like complex gradients, visual distortions, particle effects. It's advanced, but very powerful for high-performance graphics.
Wow. Okay. We started way back with the fundamental idea of bringing engineering principles to Flutter code. We dove into the, frankly, incredible efficiency of Flutter's rendering trees, explored architectural patterns, managing state, dependencies.
Talked about team practices, CI/CD, the testing pyramid, documentation.
Right. And then finished up polishing the app security, privacy, accessibility, adaptive design, even custom visuals. We have covered an immense amount of ground from these sources.
It truly highlights that building a really successful, production-ready Flutter app is such a multifaceted challenge. It goes so far beyond just writing code that works once.
Absolutely.
And the value in this deep dive, hopefully for you, the listener, is gaining that broader, well-informed perspective on all these different dimensions of high-quality Flutter development. It's about equipping you with the knowledge to ask the right questions, make smarter decisions, and ultimately build software that really stands the test of time.
Couldn't agree more. It's clear it requires really thoughtful consideration at pretty much every layer. Which I think brings us to a final thought for you to consider after all this. Given this vast landscape, we've discussed all the patterns, tools, crucial considerations like security, accessibility. How do you prioritize and balance adhering to these robust engineering principles with that constant real-world pressure for rapid iteration and getting features delivered quickly?
That's the million-dollar question, isn't it? A question every single team grapples with daily.
Indeed it is. Definitely something to mull over. Thanks so much for joining us for this deep dive into Flutter engineering.
It was my pleasure.